places where you have seen projectiles flying around through the air. A football game. The quarterback gets the ball somewhere in midfield. He's got a receiver in the end zone. He's got to launch a long range to score. Notice the way he throws the ball. He throws it up.
Very distracting.
May not be exactly 25-degree angle, but he tries to get close if he can. You know, he doesn't have time to get out his calculator and estimate the range. By contrast,
Yeah, you have. Hail Mary.
no, what is he trying to do?
Accuracy.
Maximize where he's at right now. In the old days of military gunnery, before the days of digital computers, the monkey is compared to the bullet? No. So if we were aimed correctly, bore-sighted correctly to start with, we should still hit because gravity is acting the same. A couple of years ago, I wrote a little computer program to simulate that, and I turned it into a game for little kids, so you'll have to forgive me for this, because it is written kind of like a game for little kids. So what this does is it simulates doing a strobe picture of this event. We get to... We're going to screw up your light here now. Okay.
One love.
Okay, we left off with somebody who typed in a velocity that was larger than the maximum allowed by the program. So that's why it says, give me a break, you've never even seen a musket with this much power. Type a smaller number for V. So I typed 55 in there. Let me delete that out and put in a small number. The smallest number this particular program allows is 18 for the muzzle velocity. The 0 means 0 time delay. So the monkey begins to fall. I didn't have the program draw the tree, just the monkey. He accelerates downwards because of gravity, but of course the bullet also accelerates downwards. And eventually they get hit. Okay, now being that it's a game, we have to put in little instructions so the kids can do it again. So I'll say, yeah, I want to play again. Let's see what happens if we pick a higher velocity. Let's say 22. You notice the bullet doesn't drop quite as much and the whole thing doesn't take quite as long. Occasionally, if any of you are involved in a computer class of any sort where you're actually involved in programming the computer and understanding how the computer works, the computer has to do this calculation in finite steps. And the result of the finite non-zero step size is that occasionally the bullet will pass the monkey before the computer realizes that it's been hit.
Yeah.
And so the screen display will show that. Sometimes the bullet will go on through and then later the computer will say, oh, it got a hit, and so it'll blink and give it a hit. So that may happen a couple of times on here. Let's try it again with the higher speed still than we had before. Let's go to say 40. We've got another sound effect over there that wasn't planned. Okay. Notice that the bullet hardly falls now because the whole thing is over quickly. Gravity doesn't have as much chance to act on either the bullet or the monkey. Says that false information for me. So we've got to try it with the real monkey and the real bullet and everything. So that's what's going to happen next. Is the question appropriate to our present discussion? Let's go.
Okay, I'm following what you're saying, but the thing is, the difference between a real, like a normal rifle and a musket, what would make the bullet go like that? Because I understand what you're saying, but I keep picturing the bullet going fast, straight, instead of,
A low speed is what makes it drop. Now, a real rifle bullet drops too. So if I were to shoot, say, a real rifle across the room at a target on the wall, I would have to set the sights on the rifle according to the estimated range. And what that does is it actually elevates the rifle barrel slightly. So if the target was at eye level, my sights would be aimed right on the target. But I would observe, if I looked very carefully, that the gun barrel would be slightly elevated because the bullet does drop a little. The reason you don't notice it is because it goes so fast, the whole thing is over before gravity has a chance to act very much.
So if you did that thing with the monkey with a real rifle or like a machine gun or something like that, wouldn't the bullets would just go over the
Almost.
monkey would fall, right?
Well, that would be a good question for us to answer because the monkey wouldn't have time to. Doesn't have time to fall either.
So he fires again right when the monkey falls, right?
The monkey fire.
The monkey falls when he
At the
sees
same-
the
right,
flash of
okay,
light.
So since it's a regular rifle, I would just go ahead and get it.
Yeah, the last one you saw was a realistic case. You saw the monkey only had a chance to fall a little bit because the bullet was going at a realistic speed. The first one was the one that wasn't very realistic. Now, to answer your question, however, imagine trying to fire, say, a 22 or something at a target that was 4 miles away. At that point, you'd really have to aim it up, and you probably still wouldn't make it, because it would follow a parabolic path and fall back. So it's all a matter of scale.
So, in a rifle, when the barrel's green and it spins the bullet, why?
And you may have noticed this little reed switch here on the end. When the ball leaves, the little 3/8" steel ball is what this thing shoots. When it leaves, it momentarily breaks the contact, breaking the circuit, which will hold the monkey from our electromagnetic tree, which you see right above there, about 2 inches away. Down
Oh, that's a monkey.
Now, one thing that I didn't quite know is a pretty wise monkey will adjust his little bolt to the top. Don't try to put it flat like that. Put the top like here, like that. On the knife. Once you get him up there, stay up there. I want to show something there.
Ready?
Leave me alone.
Good to see you, Doc.
Look, yeah, they're ready to run. They got nits on his butt. Look at that.
Okay, now don't get down yet. What I'll do is I'll just operate this manually to show you how the circuit works. This little power supply is powering the magnet over there right now, which is holding him up there. When the ball leaves the barrel, it will lift this little reed switch and just get ready to catch him. When the ball leaves the barrel, it lifts the reed switch and simply lets him go.
So is the aim right there? That's where aimed at his head or feet or what?
Okay, so we've got to check that now because I don't know if anybody's been disturbing this. It was aimed correctly at one time.
How do you
All you have to do up there is make sure his bulletproof vest is facing in the right direction. If it rotates around, it's not protected very much. Yeah, you just tighten the tube.
Oh, there's something.
And it looks like it's okay. We're aimed right in the middle of his bulletproof vest. This time now I'll have to load the ball holding the switch. We need somebody now that has a lot of lung power. Mine's pretty well used.
Jeff, go ahead.
He was trying to act real shy, but you notice he stood up and he wanted to do this all along. The secret now is you can't pull on this because it'll change the aim of the gun. Keep a nice zoom like the cable release on the camera. You guys watch down there. Carlos, you're in a kind of dangerous place. You know, back up here.
Kill that monkey, Jeff. Kill that monkey.
Very chill.
Come on, Jeff.
Remember not to pull that end up and you'll miss. Okay, reloading again. We'll try it.
You gotta shoot when it's.
Okay, want to do it again? Fast. Okay, remember not to move the gun.
I get faster.
Wait till it gets out of the way.
Pretty dizzy, Jeff.
Yeah, that's about as strong as it goes. Try one last time using less than the maximum now. Let's see what happens if it goes a
The
little
monkey
slower.
falls because he hears the sound and he wishes that, and then his circuit transfers over, and as the monkey falls, the bullet.
Maybe go at half power or 2/3 power or something there. And
Kill that monkey, bro.
so no matter how you do it, of the projectile. And doesn't involve making any graphs or anything, but it does prove the same thing. So that's a nice kind of experiment to do. You didn't even have to take any data. The success or failure of it depended on the validity of the theory. And since it did succeed, we've proven the theory just as well as we did. We've plotted lots of charts and graphs and done all those things. Something else, you might think that we've reached kind of an end at this point because we've successfully analyzed the motion of the projectile, but we've actually reached the beginning. Imagine a situation with a horizontal launcher like the one we had here yesterday. I take my horizontal launcher and I install it on top of a mountain. So there it is, facing this way. Here's my mountain. There's the rest of the earth. I start out with low power. Launch my projectile, follows a parabolic path. I increase the power a little bit. Still follows a parabolic path, but it's a little bit wider. You may know that a parabola is actually a member of a family of curves called conic sections. If I take a little cone, you know, you've seen these in your math classes made out of wood, it's just the curvature of the Earth's surface. That's an orbit. An orbit is a case of free fall, a special case of free fall. When you're in orbit, you are actually falling continuously. The curve of your path matches the curve of the Earth's surface. You are not in equilibrium, you are accelerating downwards at a rate equal to the acceleration of gravity at your altitude. If you're close to the surface of the Earth, still 9.8. As you go up higher, of course, it gets less. And that's the condition for an orbit. Now, it seems from the way I presented this that you must have to have some fantastic speed to do that. Well, it turns out to be pretty large, a little over 17,000 miles an hour. Before the days of rockets, that was out of reach. But of course, we've been living in the days of rockets now for several decades. It's well within reach. The only restriction is we have to get up high enough in altitude that our projectiles don't burn up because of atmospheric friction, which means that we've got to get at least about 100 miles above the Earth's surface, where the Earth's atmosphere is not so dense. And we can orbit things. The speed requirement isn't changed by much. It still is around 17,000 miles an hour. If you can get going that fast, then you will be in a special case of free fall that we call an orbit. Since the distance here never changes, then once you're in orbit, the path shape actually changes as well. The force of gravity provides the centripetal force necessary to keep you in orbit. If I write that in the form of an equation, the force of gravity provides the centripetal force necessary to keep you in orbit, which means now we understand the condition necessary to stay in orbit. Your velocity has to be high enough that it equals the square root of the acceleration of gravity times the radius of the place where you...
But you don't film me though.
Yearbook, not for her.